I'll be talking to you today about preprocessing and multiphase inference. If you haven't heard about the second, you're not out of touch with the statistics community necessarily. It's a term I'll define shortly. So today I'm going to give you some perspective on preprocessing. I'm going to give you some motivating examples for this research, a theoretical framework that Xiaoli and I are building to study preprocessing based on the theory of missing data, and a few theoretical cornerstones with some concluding remarks. So, first things first, defining preprocessing. Formally, I would call it all the transformations you apply to data for subsequent analyses. Informally, it's everything that happens before your favorite statistical model or machine learning algorithm. It's also called everything that you can't put into your NIPS paper and it gets the "we made features" sentence. So, this comes down to things like aggregation, smoothing, calibration, all that kind of stuff. It's widely considered really an art. It's domain knowledge driven. There's not a heck of a lot of theory there. What Xiaoli and I are aiming to do is to enhance domain knowledge with formal mathematical theory. So, why do we care about doing this? On a practical level, we're worried about things like destructive preprocessing. Most non-trivial preprocessing is irreversible. Assumptions are embedded in it and they matter. If you do it wrong, you're basically dead for all your subsequent analyses. And at the same time, there's a lot of promise in preprocessing. We all do it. We all use it extensively. Well, why? It alleviates complexity. We get to use smaller data sets, which when you have petabytes, terabytes, is sometimes very appreciated. And at least as importantly, it lets you separate knowledge and effort among people analyzing the data. I may not know the chemical details of a particular process going into some data set. The chemist who knows those details may not know the overarching statistical model we want to use, but we need to link up somehow. Now, for massive data in particular, this is usually the first step. You use Hadoop, you use Hive, you use whatever system you have to preprocess and extract features. If information is discarded or distorted by preprocessing, you're not recovering it later. Conversely, simple methods with good preprocessing can often beat complex methods with really complicated preprocessing. This is what Peter Norvig's been saying for several years now. Also, some previous speakers in this workshop have noted systematic errors dominate statistical noise in massive data. How do you address systematic errors? Well, as we've discussed a few times in the scientific context, preprocessing is one of the main ways to do this. You need to take into account these observation models, or sensor models, as Chris put them. And really, whether this is ultimately helpful or harmful depends entirely on what you pass forward to the next analyst. So now on a theoretical level, we're interested in this because traditional statistical theory has largely been about idealized situations. You have a model, it's the generative process for your data, you evaluate your procedures with respect to that whole thing. In practice, we delineate between pre and post modeling work, and we really do formal evaluation after pre-processing. So the goal is to build theoretical foundations for statistical practice and to close this gap. And we're trying to build this under the banner of multiphase inference, building on a foundation of the theory of missing data. Here's a graphical example of multiphase. This is actually from some of my genomics research. Each of these steps would be a phase that feeds information forward to the next one, which is going to produce some output. Eventually, you get the scientific problem solved, hopefully by the time you get to there. Why is it multiphase? There's multiple phases. Hence, the nomenclature. Congratulations, you've expanded your vocabulary by n equals 1. So a few motivating examples here. We're going to start with solar data. On a side note, one of the great perks of working with astronomers and astrophysicists is they have great pictures and they're all public domain. So As we've discussed previously, especially with Alex Sazalay and Joey Richards' talks, preprocessing is really ubiquitous in massive data astrophysics. Without it, you don't get anywhere. This is especially apparent for two solar observatories that are currently in use, and, well, first one's in use, second one's being built. These are called SDO, Solar Dynamics Observatory, and ATST. It's not a Star Wars reference, it's Advanced Technology Solar Telescope. These get terabytes of data a day. We're already at these volumes without having LSST or the other big systems that were mentioned previously. For SDO, the raw data exists, but it's essentially inaccessible to the community. For ATST, it will not exist. The raw data coming off of the sensors in that telescope is so big that they are going to be processing it before they store it. As you might expect, the solar science community is not entirely happy with this situation. If there are errors in the calibration, if there are any missteps in that processing, well, so much for a few $billion. Another example, continuing the trend of beautiful pictures, comes from indirect observations in astrophysics. This is about dust clouds. These are where stars are formed, it's where planets are formed, so people are very interested in them. They want to get a sense of what their dynamics are. And one of the really key relationships is between the density of the dust and its temperature. This determines whether you get cold things aggregating or hot things. Well, you don't get to directly point a telescope at the sky and say, what's the density and what's the temperature? You have to do some processing to extract these. How you do that processing matters immensely. You do it wrong, you get the entire relationship between temperature and density backwards. There's a literature in the astrophysics community about this, great papers by Brandon Kelly and some of his collaborators. It's a really nice example of preprocessing gone wrong. Another example that may be a little more familiar to some people in this room is high throughput biology. Modern technologies, we get to measure thousands of genes and proteins at a time. Two of the favorite technologies on the genomic side are microarrays and sequencing. So for a microarray, you measure the brightness of points on the array. This is what it actually looks like, it's not all red and green. This is what the machine reads. And you use that to infer things like gene expression. And of course, sequencing brings its own extremely complex error processes. For now, I'm going to focus in on microarrays. So with microarrays, their standard methods rely on very heavily processed data. The raw signals are corrected for background contamination, they're normalized, they're recalibrated, and then the statistical analysis unfolds and you get a p-value. You might ask, why don't we just build a big joint model of the whole data generating process? Or at least if you come from Harvard, that's what you ask. Well, a couple of things to note here. Computational scale would be large. The measurement processes are extremely complex, and they each have their own set of domain experts, essentially. And that means we need to have this separation of knowledge and effort. It's a lot easier to get some software that has all those experts' knowledge embedded in it and simply use it as a standard in biological workflows than to go and actually start building a joint model with them. So what's really missing when you look at a problem like this? What's missing when you look at this microarray analysis? Well, a few things. From a lot of these low-level processing steps, you don't keep measures of uncertainty. This is very typical, and typically these calibrations are irreversible. The processed results are actually in themselves usually insufficient for follow-up. You actually see papers saying, based on a particular statistic, we can't tell if it was high to low, low to high. And you keep going in that direction. A nice example of this is really given by the background correction step. Suppose that you have some observation. This could be the intensity off of an array that consists of a signal plus a background. Typical practice, you correct for B somehow. It could be a model, it could be some ad hoc adjustment. You pass only point estimates forward of the log signal. As you might expect, this could lead to some issues. You're discarding a lot of variance information here. So you don't have a good sense of how uncertain the really low values are. When you go through and try and assess changes in the gene expression between conditions, this can backfire. So the basic remedies, you of course want to wring rich summaries from your observation models. You want to retain summaries of uncertainties. And I'm very fortunate to be in the last session here because I get to leverage previous speakers. And I think Rick Stevens' proposal about replacing alignments in high throughput sequencing with graphs that have associated probabilities, really capturing that information, is a fantastic example of this. And you really need to integrate this richer information to the downstream analyses better. A lot of methods are essentially built downstream to handle much simpler input than they really need to. So that's why we care about this, and that's some actual problems. We're now going to turn to the theory. For the theory, we're starting to build a framework for formal evaluation of pre-processing procedures as part of a holistic analysis. So what this really comes down to is a fairly simple model of the type that you see with most missing data contexts. There's actually two models. One of them is the data generating process. The other is the model facing the downstream analyst. Just some notation. Y here would be the observed data. X are scientific variables of interest. Theta are parameters governing scientific processes. T is the output from the pre-processing. For the data generating process, this is the model facing the preprocessor. We have conditional independent structure between these two sets of random variables. And this also essentially corresponds to the separation of knowledge. You typically have domain experts who have excellent knowledge about this, may not know about the scientific model here, and vice versa. And here we're talking about X, these scientific variables we care about as the missing data. For downstream analysts, their situation with respect to missing data is different. They get T, which is some pre-processed version of Y. Could be deterministic, could be stochastic. And they are facing X and Y as missing data. Just to give you a sense of how this framework works, when you're talking about the problem of indirect measurements in astrophysics that I mentioned previously, Y would be the measurements from the telescope. X are the true features of the dust cloud. You could think temperature, density in different areas. The PY distribution is the observation model characterizing the telescope's response to incoming photons. PX and theta characterize the dust cloud and the dynamics happening there. And conditional independence works pretty well when you're separated physically by light years. For the microarray measurement errors, Y are the actual signals that you would see from the array. X could be the true gene expressions. PY characterizes the measurement process, and PX characterizes the biological process along with theta. Once you have just a basic model like this, you have to go through and start thinking about what's a multi-phase estimation procedure and how can we start to reason about it formally. This is surprisingly tricky. Just to start, we're going to say that the first phase, the preprocessor, provides T, which consists of some estimator for X and some supplemental information. The second phase has some estimator for theta based on this statistic, and different practical constraints on the preprocessor induce different output. What this means is the second phase has to adapt. So the second phase analyst, the downstream analyst, will adapt to the input they're given. For instance, you may have just giving point estimates leading to a simple mean, point estimates with weights lead to a weighted mean. This is somewhat different from a lot of the work done with multiple imputation, missing data, where you assume fixed second stage procedures. You can, of course, extend this to more than two constraints. You could think of aggregating spatial data, maybe at different levels of resolution. And you really have to regulate this adaptation. You have to, and for example, you should do better if I give you higher resolution data. Well, this adaptation is actually somewhat difficult to regulate. You want to improve performance with more information, and there's a couple of ways you can do that. The weakest condition you can possibly think of, theoretically it makes sense, is what we call risk monotonicity. It simply says, if I give you deterministically more information, you do better. Great. Even better condition is something that Xiaoli developed in 1994 called self-efficiency. This means you can't do better by taking an estimator based on less data and smushing it together with an estimator based on more data. Seems like a pretty sensible condition. It actually can be violated quite easily if you're not working from certain classes of models or estimating equations. In the multiphase setting, this is a very strong constraint on mutual knowledge between the preprocessor and the downstream analyst. There has to be enough mutual knowledge there to prevent any misuse of additional information given to them, at least when you're building the theory. Otherwise, you're pretty hopeless in terms of getting actual results. Some ways you can generate these procedures: all of the statisticians' favorites, Bayes rules, MLEs, at least asymptotically have this property, and in general, models with principled probabilistic estimation strategies can act as generators for such procedures. Now, it's important to note that this is by no means the only way to generate such procedures. It's just, in my mind at least, the easiest way to think about it. Something else to note here: constraints are at the heart of multiphase theory. You get a lot of dead ends and essentially trivial results if you don't think very carefully about the practical constraints of the problem. For example, if I simply say there's somebody giving me some data and I have an analysis I want to do, what's the optimal thing to do? They have the data, they do the analysis, they give me the answer. Sounds wonderful, but it's not an extremely useful theory when you're thinking about building scientific repositories. However, these types of pragmatic constraints can yield deep, rich theory, as we've seen for multiple imputation in statistics, as we've seen for missing data and some of these other problems. This really comes down to the idea of building dual-use data sets in the first phase. If you could target a particular analysis, it's really easy. You do it. But we really want the pre-processed data, these repositories, to be good for multiple uses. You want it to essentially act as an estimator for X, using the previous notation, and to be useful in future analyses. So you're looking for interpretability, modelability, not just statistical efficiency here. Two types of constraints that we're investigating for multiphase. One I like to call not too much extra work, because that's usually what I have to tell my applied collaborators. Essentially, it can require the complete data estimator, so what the downstream analysts would do if they actually saw X, to be nested within what they would do if you give them supplemental information. Again, think weighted regression and unweighted regression. Another one involves distribution of effort. You could require, for example, that the first phase preprocessing can be distributed across researchers. And this essentially boils down, in a model-based setting, to building preprocessing from factored models for X. So I'm now going to show you a basic type of result you can get with the latter constraint involving sufficiency. So suppose that we have a problem. We want to distribute preprocessing across multiple researchers, each of whom are doing their own experiments. We're going to, for the moment, consider a particular model, px given theta. Very basic question you could ask. How can they determine what's needed to maintain sufficiency for theta? They may not all know the complete model. They all have their own experiments, but how do they determine this? Conversely, given a particular preprocessing that these people will choose, what models will they be safe for? What will they maintain sufficiency for? So, to start formalizing this, we'll assume that the observation model factors by researcher. It's pretty reasonable. If they're in physically separate labs, hopefully we can get such an assumption. Then we're going to introduce a factored working model for X called PW. And we're going to introduce some working parameters called eta, separate by researcher. Each researcher then models only their own data, just simply marginalizing over the X's, and they get the implied distribution of Y given eta. They pre-process their observations yi into separate ti's. And we're going to say these are really good researchers. They have the training of at least 3 statistics classes. So they're constraining ti to be sufficient for eta. So when will the working model preserve sufficiency for theta? Formally, when will we get sufficiency for eta implies sufficiency for theta? Well, obviously, it's not enough for the working model to be correctly specified for each yi. A sufficient condition is this. If you can generate the actual distribution of X as a mixture over this product distribution with respect to a density over eta given theta, you're good. Nice. So it's not enough to reduce the data based on a correctly specified model. You've got to look to other things that include it hierarchically as one direction. But you can get these results without keeping everything you need to be sufficient for X. Note I said it was sufficient, not necessary. There's a few counterexamples that you can get to the necessity of this condition based on essentially unparameterized dependence. They're basically statisticians' favorite hobbies. You take a couple of normal random variables, link their signs, and mess with undergraduates. That's the kind of thing that suffices here to give counterexamples. A couple of other ways that you can apply classical theory to this, just to give you a flavor of what we're starting to do. One of them is about looking at doing the best with a particular preprocessed input, essentially evaluating preprocessing methods on this type of criterion. So for fixed preprocessing, we want to know what bounds the performance in a variance sense, at least asymptotically. And it turns out in large samples, a quantity called the fraction of missing information, which is given by it's a matrix given by a nice function of a couple of information matrices, determines a lower bound on the variance. Formally, you get relative excess variance converging to this fraction of missing information. A couple of things that come out of this. For one, you can use this to compare preprocessing methods. That's pretty clear. The other thing that's interesting, though, is what happens to this when you start attempting to target different functions of theta. Under transformation, this F matrix can change rather dramatically. And this actually shows, it gives you a sense of how well targeted versus how broadly targeted a particular method for preprocessing is. Another direction you can go, you can say, fix what my downstream analyst is going to do. They're stubborn. They're going to use proc blank. I can't change anything. What's the best I can give them? It turns out all admissible with an asterisk rules for generating your preprocessed output are Bayes or generalized Bayes. The star, of course, pertains to all the irregularity conditions that would require another 2 people slots, I believe. This is essentially an extension of standard complete class results that any of you who decided to persevere long enough in statistics may have avoided. And you can also obtain further tighter bounds from the theory of multiple imputation. For a given amount of data you're passing forward, what can your performance be? So, to wrap up, I've given you a sense of our goal. We're trying to build a foundation for multiphase inference. It's descended from the theory of missing data. You could probably tell that by my resemblance to a missing link. And it's motivated by real problems and practical constraints. We're trying to bridge statistical theory and practice. We're trying to do this by building a formal framework for multiphase theory. We've got a model for this. We have multiphase procedures, and we're beginning to establish the constraints that are crucial for building a deep theory. And we've also established some theoretical cornerstones with conditions for distributed preprocessing and some performance bounds. Coming attractions. Well, for theory, the real first goal is evaluation of preprocessing methods for design and analysis. A lot of this is targeted at building scientific data repositories. We're also looking for constrained optimality results for broadly applicable multiphase strategies. For applications, I'm actually working on 2 of these areas at the moment. We're trying to improve multiphase methods for biological and astronomical problems. In particular, solar astronomers are eager to try and sort out ways to safeguard themselves as they deal with these terabytes to petabytes of data. On the biological side, it has a very direct impact on research I'm doing in both genomics and proteomics. And for computational strategies, we hope to use multiphase to help build computational strategies for massive data. On that point, the real goal is to follow a trajectory much like multiple imputation followed. Multiple imputation was originally a technique to enable practitioners to go out and run analyses themselves without bugging statisticians. Eventually, though, even statisticians started using it as a computational tool. The key reason for that is once you understand the error properties and limits of a method, you're much more comfortable using it as part of your core toolkit and really exploiting it. That's what we're hoping to eventually get to with multiphase inference. Now, a few acknowledgements. Of course, my primary advisor, Xiaoli Meng, my co-advisor, Edo Araldi, who a few of you may know, I'd also like to thank Art Dempster and Stephen Blythe for their support in this, and of course the entire Harvard Statistics Department who have generously spent a few years putting up with me and training me, and of course, most importantly, the people providing the money, the NSF. Thank you very much. He's asking if we've thought about the data quality issues facing data warehousing type systems where they have automated pipelines, they want to detect the origins of faults and things of that nature, correct? We've considered that a little bit. Most of my collaborations have been more scientific than industrial, which is why I haven't pursued that direction too much. I think it's a very interesting direction to start looking towards because there's, I think, a great potential to, how do I put this? To formalize some of the tricks that have been both successful and in some cases stellarly unsuccessful in that context.